In this lesson, we'll show how to find the location of the centroid for an area using the method of integration. For example, consider this member having a cross-sectional area that you see here, defined by a bounding curve. If we know what this bounding curve is, we'd be able to find the centroid location for the area of this cross-section. And that would be important if we ever want to find the stress that acts in the member when it's subjected to a loading. Now, to solve problems like this, we can do so using a single integration rather than double integration if we consider rectangular elements. For example, consider this area. A rectangular element that we could use would be a strip that's in the vertical position. We have to remember that this strip, or rectangular element, has to intersect the bounding curve at the arbitrary point. In other words, a distance of x over and a height of y. Once these dimensions are shown, then we can determine the area of the element. For example, here it would be a height of y and a thickness of dx. Also, we need to know the location of the centroid for our rectangular strip. And that, of course, gives us our coordinates, x tilde and y tilde, in our formulations down here. Here, of course, our distance x tilde is equal to x, and our distance y tilde would equal y over 2. Rather than using elements that are vertical, we can also solve the problem by using horizontal elements, like this one. Again, it has to intersect the bounding curve at the arbitrary point. In other words, x over and y up. Again, once these coordinates are defined, then we can define the area of our strip. Here it's equal to x times dy. The centroid location for our rectangular element, of course, is a distance of x tilde equaling x over 2 and y tilde equaling y. So knowing our area and x tilde and y tilde, as we've just stated, we can carry out the integrations and we can solve for x bar and y bar. Let me demonstrate these ideas with a few examples. We'll begin with this problem, where we want to determine the location of the centroid for this area, and we want to choose elements having a thickness of dx. Do you see the element on the area? It would look like this, won't it? It has a thickness of dx. Of course, the element intersects the curve right up here at this point, and it has a centroidal location right here. This point is the arbitrary point. In other words, the distance x over and y up. Now that it's been defined, we can now find the three things we need to carry out the integrations. First, x tilde. That, of course, is the coordinate location from here all the way to here, and that's equal to x. Now we have y tilde. That distance from here to here is simply equal to y divided by 2. Since we're going to be integrating with respect to x, we have to now write y in terms of x, and that's pretty straightforward. It's simply equal to x squared divided by 2. Of course, y is equal to x squared, and that's why this is true. Finally, let's get our area dA, and that's equal to y, the height of the element, times its thickness, dx. Again, expressing everything in terms of x, we have x squared times dx. Now that all this is set up, we can now apply our equations and get our results. Let me demonstrate that by finding x bar. Here we have x bar equaling, and there we have the integral from 0 all the way to 2, we're summing on x, remember, of x tilde, which is equal to x. And then we have our area, which of course is x squared times dx. Down in the denominator, we simply sum from 0 to 2 our area, which is x squared times dx. Now that this is set up, we can proceed to go ahead and carry out the integrals, and this is pretty straightforward, isn't it? When you work it through, you get your result of 1.5 meters. Of course, we can get y bar in the same way. Here, of course, we would put in y tilde, which is equal to x squared divided by 2, and dA, which is x squared dx. And down here, of course, again, x squared dx. If you want to stop the video and carry out the integrations, you'll be able to check the answer of 1.2 meters for y bar. By the way, once you get your results, you should see if they make sense as well. Here, you can see that x bar is located a distance over this way, about right here, 1.5 meters. And of course, y bar is a distance up. 1.2 meters brings us right here. That sort of makes sense as to where the geometric center of this shape really would be. All right, now let's solve the same problem, except here we'll use elements having a thickness of dy. Do you see this element on the area? It looks like this, doesn't it? Of course, it intersects the bounding curve right here at this point, and of course, here's the centroid for our area element. We need to define the location here, of course. It's at the arbitrary point, isn't it? So this is x over, and of course, it's y up. We can now define our three things that we need for our integration. And to do that, we need to find this distance first. What do you think that would be? Well, this distance is 2, and this distance is x. That makes the distance equal to 2 minus x. Now let's figure out what x tilde is. That's the distance from here all the way to the centroid of our element. How much is that? Well, it's x plus 2 minus x divided by 2. So let me write that in here. X plus 2 minus x divided by 2. Of course, if you work this through, you get the following. It becomes 2 plus x divided by 2. Since we're going to be summing along the y-axis, we better express this in terms of y. Therefore, we can write this as 2 plus the square root of y. And of course, it's divided by 2. Now let's determine y tilde. That's the distance from here all the way to here, and of course, it's simply equal to y. Finally, we need to define dA. What would that be? It's 2 minus x. And this is multiplied by our thickness, which is dy. And again, we have to express our area in terms of y, and therefore we write this as 2 minus the square root of y. And then we have our dy, of course. Now everything is defined here, and we can proceed to go ahead and apply our equations. Let me show you how we can find x bar. Here we would write x bar equaling. Now we put in our terms. We're going to sum from 0 all the way to where? To 4, right? Because we're summing along the y-axis. We have our x tilde, which is equal to this. In other words, obviously, by just simply multiplying these together and then going through term by term to integrate here and, of course, down here. Or you can use your pocket calculator. Anyway, you will get the same result as we had gotten previously using elements that had a thickness of dx. The answer is 1.5 meters. So when you set up the problem, in some cases the element will make it easy to integrate, and in other cases it'll make it more difficult, as in this case. You can also find y bar, and of course you do that by simply taking y tilde, in this case y, and putting it into here, and taking your dA element, putting it into here, and also down here, and carrying through the integration to get our result of 1.2 meters. You may want to stop the video and carry out the integration just to check the work. Now let's flip it around a bit. We'll use the same curve here, except now we'll consider the area in this region rather than the region over here. Here we want to find the centroidal location for this area using elements having a thickness of dy. Do you see the element on the area? Here it is. Here's the intersecting point with the bounding curve, and of course here's our centroidal location. We need to define this location as being the arbitrary point, x over, and of course y up. Now let's define our three things that we need to carry through the integrations. First off, we have to get x tilde. This is this distance, and what would that be? Why, it's x over 2, isn't it? And since we're going to be summing these along the y-axis, we have to express this in terms of y. So therefore we write this as the square root of y divided by 2. Next we have to determine y tilde. What's that equal to? The distance from here all the way to here, and that would equal y. Finally, we need dA, and that would equal what? That's x times dy. But again, we have to express everything in terms of y, and so we write this as the square root of y times dy. Now that we've defined the data we need, you may want to stop the video and put this data into the equations and carry through the integrations. Of course, here you're going to integrate from 0 all the way to 4 and show that you indeed get these results. X bar is 0.75 meters over, and y bar is 2.4 meters up. Now, rather than solving this problem using elements having a thickness of dy, let's try to do it using elements of thickness dx. Do you see the element on the area? It looks like this, doesn't it? Of course, it intersects the curve right here and has a centroid right here. Now we just have to define the location of this point. Of course, that's the arbitrary location, isn't it? In other words, it's a distance of x over and y up. Now we have to define the three things we need in order to carry out the integrations. Here, of course, we'll need to know the height of the element. This distance is how much? Well, it's 4 meters from here all the way up to here, and this distance is y. Therefore, our answer would be equal to 4 minus y. Now let's work out x tilde. How much would that be? Well, that's simply equal to this distance of x. And now we need y tilde. What do you think that would be? Well, that's y plus 4 minus y divided by 2. And of course, we can simplify this and rewrite it in the following way. 4 plus y divided by 2. If you think about it, this is the average distance. In other words, if this height is y and this height is 4, the average distance is 4 plus y over 2. Finally, we have to express everything in terms of x here because we're going to be summing along the x-axis. So let me rewrite this as 4 plus x squared. We'll divide this by 2. Finally, we need to find dA. And what would that be? Well, I hope you said it was 4 minus y. And of course, we multiply this by dx. And we have to express everything in terms of x. And so let's finish this up by writing it that way. 4 minus x squared. And then we have dx. Now that everything is set up, we can now apply our equations, and we can solve for x bar and y bar, as we did previously. But in substituting this information into these equations, you'll have a bit more work in terms of the integration. But at any rate, if you carry it through, you will get the same results as we did previously. And they do make sense in terms of geometrically where the centroid for the area is located. And so having completed the problem, we'll end our lesson.